Okay, thanks, Adam, and thanks, Christopher. You guys can hear me, hopefully, for allowing me to speak here. Doing AAG, the Dendro sessions are always one of my favorite things to go to, even though it's not really my field. So I was really happy to get to be part of this. But yeah, so my talk is kind of looking at dendrochronology compared to remote sensing from a remote sensing perspective. So I'm a remote sensor at heart, and kind of looking at how we can compare tree rings with Landsat, which is a satellite that I use in a temperate forest context. There we go. So I just wanted to show this picture. This is actually, I kind of find this picture funny because this was the first time I ever worked with tree rings. It's also the last time before this project I ever worked with tree rings. This is actually me during a fieldwork season. In my master's, I was helping out some colleagues with some tree ring work. And it's kind of what got me interested in tree rings, and kind of I'm happy to have a chance to work with them again, kind of 4 or 5 years later. So, but my main work is working with Landsat. If you guys don't know, it's a satellite that is been flying, or kind of the satellite constellation has been flying around the planet since 1972. It kind of sports a 30-meter spatial resolution, which means that each pixel is 30 by 30 meters in size. So it's a pretty high resolution sensor for a global platform. It has a global coverage, so it covers the Earth. It has a 16-day revisit time, which means that every kind of 16 days, it kind of revisits the same area. So what that means that every summer you can get multiple images, and you can rely on pretty consistently on getting at least one image, one good data point at least per year, and hopefully multiple data points per year. And one thing about Landsat has visible bands, like you can see in a color photograph, but also near infrared, which is great for vegetation, and shortwave infrared, which is also really important for monitoring vegetation in kind of supplementing the near infrared band. And one thing I also want to talk about is the kind of the recent stuff with Landsat is that there's been a lot of work into sort of consolidating these different satellites that have been flying since 1972, because many of them were constructed in different years, and they're very different in terms of how they were built and how they record data. But there's been algorithms that have tried to connect them and make them more standardized, that we can be sure that a data collected, early in the time series can be linked to data collected late in the time series. So the keys here is kind of having a standardized time series through time, so that we can be kind of more sure that the change we're seeing in the land is real change, and not kind of fake change due to sensor noise or atmospheric effects or things like that. So kind of what we see here is we have data, kind of like satellite data on the y-axis here, so what we call vegetation index, which is some sort of quantification of vegetation from the satellite, and we have a time series through time. This happens for each pixel, right? And similar to our tree rings, we kind of fit a model to it, right? And we can have a set of parameters, and we sort of find in this case, it's like a piecewise linear function, but we can find a way that a set of like simplified results that kind of explain the story that pixel is trying to tell us. And so that kind of got me thinking, oh, maybe tree rings will be a good kind of comparison point for this. And I'll talk a bit about more of that as we go forward here. So under the hood here, this is kind of just showing an area of Southern Ontario, Mississauga, west of Toronto, that shows kind of vegetation change over time at a yearly interval using this Landsat data. So black areas are areas with less vegetation, white areas with more vegetation. Hopefully you can see my cursor here. So you can see things, these are some of the fitted time series for these different colored squares here, which are different pixels. You can pick up things like the blue and the yellow square are neighborhoods that were built, and then you can see them starting to green up as vegetation, kind of trees are planted, yards are grown, and things happen as the neighborhood kind of matures. And more recently, we see this side. This is actually a conservation area that has trees, and you can actually see the impact of emerald ash borer, which is a pest that comes in the late 2010s. You actually start seeing it starts to gray up here in the last couple of years. You start to see it happening right around now, which happens when the kind of the pest comes in and starts destroying the forest canopy for those ash trees. And so that's kind of what we're seeing. That's kind of the Landsat data. My first question, I work really closely with conservation agencies and different municipal governments, and they always want to know, okay, we see these vegetation index, we see Tesla Cap angle, which is the one I use, or NDVI, which one you might have heard of. What do these values actually represent on the ground, right? So we have a vegetation index, and we have it through time. We have changed some unit of that index. But what does it actually mean in terms of real change on the ground? So the first kind of step here is what we call ground validation, which, kind of we go on the ground and we kind of cross-reference with the satellite data and understand what that change represents in a real on-the-ground variable. So I'll go through this quickly because it's not kind of core to the Dendro talk, but just so you know about it, I went to all these sites across the Credit Valley watershed, Southern Ontario, and collected these things called hemispherical photos at different forest types across the watershed. These hemispherical photos, they're like 180-degree photos of the forest canopy, and we can use that to estimate things like leaf area index, percent canopy cover, and others at these different kind of types of forest sites. I collected many hundreds of these photos, and pretty much the takeaway you need to know for this talk is that there is a strong relationship between kind of the satellite-derived index, the Tesla cap angle in this case, and percent canopy closure referenced from these hemispherical photos. And so we can pretty confidently say that the more Tesla cap angle we have in these dense forest canopies, the kind of more dense the forest canopies are. And so I use this to kind of understand change through time rather than on the Landsat variable, in an on-the-ground variable in terms of our Landsat-derived percent canopy or percent canopy closure, percent canopy cover. So we can start understanding the changes through time, right, since 1972, using this long-term Landsat data at different forest sites. But the next question here is the one that's kind of core to this talk is this change we are observing real? So we know that there's some real on-the-ground variable that relates to our change at a certain year and time. But if there's, say, a small percent loss of some of this variable, how do we know that change is real and not kind of the noise due to kind of differences in the satellites or atmospheric effects or time of the year, slight difference in time of the year, things like that. And so like with kind of big standard placing disturbances like, development, suburbanization, or fire, which is the project I'm working on separately from this, we have a really good data, and we can use that to cross-reference and make sure our time series change is real, right? Like we have databases, people like government agencies keep track of when there was a fire, where there was a fire, and they keep track of where there was development and when there was development. So we can take those locations and those times, we can cross-reference with our satellite data and understand, we can make sure our changes, how often our change gets understood and what percent of that change is real or fake. But what about kind of, I call it change validation. That's kind of my kind of coin term for it. Well, how do we know that, say, like a small percent change, like say like ice storm damage, or even like natural things like just kind of the gradual changes of growth and decline as a forest gets older or a tree dies and replaced with a new tree that grows. These kind of smaller level and kind of more local scale changes, how do we validate those changes when we don't have those kind of government databases to kind of reference and use it to back up our results? And so that kind of brought me back to dendrochronology, and I was thinking, dendrochronology, kind of similar to remote sensing, provides kind of this yearly chronology of forest change at an annual resolution. There's some disconnect, right? They measure slightly different things, like the canopy versus, the kind of the entire biomass of the tree or whatever. But there's some sort of relationship there, and studies have shown that in different places. But doing some research on those different studies, I kind of came to the conclusion that almost all these studies that compare remote sensing with tree rings, they focus on kind of these northern boreal environments, especially in Alaska. There's a lot of great work out of Alaska and the Yukon. But there's a lack of study focused on kind of temperate, kind of deciduous and mixed forest environments like I have here in Southern Ontario. The next thing was almost all these studies use the broad-based kind of AVHR platforms that have like 1 kilometer or 2 kilometer or 8 kilometer spatial resolutions. And there's really no use of the Landsat in this context, which makes sense because a lot of these people are coming at it from a dendro background where they can just take the kind of finished product and use that to compare with their tree ring data. I'm coming from it from the remote sensing background where I have the kind of more advanced knowledge of remote sensing and can compare it to my tree ring data going the other way. So it's kind of an interesting, different kind of a difference of perspective, I think, kind of leads to this difference in data usage here. And then I found there was little study on any index besides NDVI. And the thing with NDVI I found in my past research is that it's known to saturate, so it kind of levels off at really high biomass environments. But indices like Tesla cap angle, which is the one I use for this study, incorporate the shortwave infrared band, which helps it kind of not get saturated at those high biomass environments. And so maybe we can get better relationships if we use a different index besides just NDVI. Okay, so with dendrochronology, I visited these kind of 16 of those same 30 sites I went for hemispherical photos. I went to those same sites across this kind of urbanized watershed. So we have some urban sites and some rural sites. In the summer of 2018, I got permission from the local agencies and the city governments. And I collected, I'm not gonna go in detail here, but I went to these sites and I took some fun fieldwork photos and collected pretty much all the canopy dominant trees in a certain area kind of within this 3x3 Landsat pixel window, kind of in the center of this pixel window. And from these 30 sites, I collected 2 tree rings per tree. And then I compared those, I'm comparing those with the kind of Landsat record at that point. And then kind of what I use, maybe this is, I don't know if this is the method most people use in the field, but I heard about Coup Recorder and I've been using that. So I scanned my tree rings at kind of a high resolution and then I've been cross-dating in dplyr to kind of check for kind of those rings that are 1 or 2 years off in certain ways. So it's probably all kind of old news to you guys, but for me, it's been really fascinating kind of going through this process. I'm making my subset chronologies and right now I'm in the process of kind of testing some of these different standardization methods for the sites that I finished. One thing interesting I want to talk about here was in many of my sites, 1988 was a key kind of narrow marker year. And that's also one of the narrow, kind of the lowest vegetation years I've been seeing in my Landsat data. So that was kind of my first sign that maybe we're on something here, that we have a narrow marker year and a very low kind of productivity year in the Landsat record. So that was kind of where I started. And then I started building actual chronology. So I'm just going to show 3 examples here. This is a deciduous forest site, and kind of to start us off, I just kind of have the raw data just to kind of show it. We have the kind of the millimeter data. Some of the sites kind of interesting. They kind of work at a 1-year lag, and some of them work at a kind of a no-year lag. So I'm still playing around with, like, is there some consistency here, or is it site dependent? And again, this is just like the tree widths in the green, the Landsat derived canopy cover in the red, and then I have sample depth as well. You can see that kind of on the top there, and then time on the x-axis. And you can start seeing, like, oh, maybe, you know, it doesn't maybe relate so much in the beginning, but as you get to these kind of more recent years, we see kind of similar dips in the record, and kind of similar, they follow a similar path maybe in the more recent years. And so I kind of did that for a couple other sites just to show it off. In what we see here, this is a coniferous site, a cedar site, and we kind of see some interesting things. So what I did here, what I started doing was play around, like, oh, I'll fit it to a certain thing in dplyr. Spline is one of the methods they have. And what I did was I took the Landsat data and did the same thing. I fit it to the same spline line. And I find, oh, like when you fit the data to the same kind of method, it starts to line up really interesting in like an interesting way that maybe shows a sort of pattern here. So across this entire kind of overlap area between the tree ring widths and the time series, we can see that they follow a similar pattern of kind of periods of growth and decline, or increase and decrease. And I don't know what the proper way is for measuring kind of comparison between these kind of time series, but I just did a simple, for this kind of presentation, I just got a simple R² between the 2 data sets, and you can see that has a significant R² at 45% variance explained. So I don't know if there's a better way. Maybe people can comment on that, but that's kind of what I just did for quickly a year-to-year comparison between these 2 data sets. I wonder if there's some sort of like fuzzy, kind of more all-encompassing method you can use to compare them at a more, maybe a not year-to-year level, but that's just kind of the way I did it for this point. Then the last one I want to talk about here, this is a coniferous plantation, a pine plantation that was actually planted in the early late 1970s. And we can see here is that in the kind of early growth years, they follow a different pattern where the Landsat derived canopy cover is increasing as the forest grows, but as the fitted data kind of, or the tree ring data is like decreasing as the tree kind of gets older and older from that initial growth period. And this one's interesting. This was a -1-year lag, while the last one was not a -1-year lag. So I'm still working with that kind of question there about the lag period. And interesting is that it gets a bit noisy in the middle here, but in the end period, it seems to follow a really similar pattern with an overall R² of 30%. But in the last kind of 10 years, we have a pretty strong relationship where you can see it clearly follows the same kind of periods of growth and decline in those last kind of 10 years between 2005 and 2015 at this coniferous plantation site in Southern Ontario. So just kind of the takeaways is that I'm still kind of obviously in the midst of this project. I still have like 6 or 7 more sites to kind of measure and go through, and a bunch more sites obviously to kind of do the standardization process for. And I'm still kind of working through what standardization method I should use and kind of the proper way to do these things. But I think there's some interesting possible connections here between the remote sensing data and the Landsat data that I can hopefully build upon and use maybe as a validation method for the Landsat data in these kind of more interior forest environments where we might not have you know, government data or known events to kind of cross-reference with our remote sensing data set. So it might be a key change validation tool that might increase the confidence in these remote sensing results and be a useful thing. So I want to thank my funding partners, government agencies that helped me, and those people that helped me in the field and with advice and things like that. And yeah, that's it. Thank you so much.
Thanks, Mitchell. If we have any questions, people can please type them into the Q&A and I will read them off as they come in. Oh, here's a couple. So somebody asks, are the R² for the smooth data or for the annual ones?
I did it for the smooth data. I actually did the R² like just the other day because I wanted to show some quantitative measure. I'm still, as I said in the thing, I'm still not actually sure, you know, what's the what in dendro field, what you guys use to compare 2 different chronologies and what the proper method is. I just kind of did an R² because that's what I know to do really quickly. But yeah, it's from the fitted kind of mean data rather than the year-to-year noisy data.
Somebody also asks, says that's a lot of data for hemispherical photography data. Which programs did you use to process them? And is there a way to batch process that data?
Yeah, I did that like 2 years ago. Let me look up. I think it was, what was it? Dendro.ex, or sorry, DHP.exe. It's actually a Canadian government program that I had to, it's not available like out there. I actually emailed someone at the Canadian government and they gave it to me. And it doesn't do batch processing per se. Like you can run with certain values and then it will kind of, you can use those as like the default and you can just adjust them as you go. I actually had an undergrad help me he had a summer job to kind of help me with the canopy cover estimates from those. So it was photo by photo, but it was like some defaults you could put to kind of facilitate the process of finding those breakpoints between sky and leaf in the kind of the binary, the black and white versions of those photos. But it's called dhp.exe.
Somebody asked, what do you mean by %CC?
Yeah, so that's percent canopy cover. That's based on those those hemispherical photo analysis. So percent canopy closure, I guess, is technically the term from, it's pretty much the percent in these photos, percent of the white sky versus the percent of the black kind of leaf and other, leaf and wood parts of these kind of hemispherical photographs.
Okay. And last question, which season NDVI do you use?
Yeah, I mostly use midsummer. So my data set usually start collecting the data for the time series from like mid-June, like June 15th-ish to like August 25th. It's kind of the range. So we try to hit that peak growing season and try to minimize the effects of seasonality.